All right, let's talk about chapter 10, which is on beaches, shoreline processes, and the coastal ocean. Okay, so the coastal ocean, 50% of all of the human population on Earth lives near a coastline. So that's usually within, say, 50 miles of coastline. 50 miles? No, sorry. Your textbook shows tells you of a specific range. It might be 20 miles actually. But essentially, majority of the population lives near a coastline. 95% of the fish caught within the ocean is within 200 miles of the coastline. So that means almost all of our seafood resources that we get is caught by the coast. And the coastal ocean supports huge biological productivity and biodiversity, which includes wetlands and estuaries. So these regions on the coastline produce a lot of seafood resources as well as biology. It can support huge amounts of biology. So here are the three main regions within the coastal area. So you have your shore. So your shore is the zone between the lowest tide level, so basically your low tide, and the highest elevation of land affected by storm waves. So this is not just the waves that affect the shoreline normally. This is when you have extremely high waves due to storms. So that's usually near the back part of the shore. So in this case right here, in the image below, you can see that tan part where they depict the beach at. And then there's those cliffs. So it's basically at the base of the cliffs is the edge of the shore, and you have to go all the way out to probably where it says breakers, right after breakers, and that's where your lowest low tide is at. So that would be your shore. And then you have your coast, and your coast extends inland from the shore. So this one goes all the way inland as far as the ocean related features can be found. So in this case, if you have like sand berms or marine plants, that's still part of your coast. So essentially you have to go all the way in until you can no longer see any features that are related to the ocean. And your coastal area goes all the way out to in the ocean to probably right before it goes down into the deep ocean. And then your coastline is essentially the boundary between your shore and your coast. So in this case, your coastline would be, let's see, where is it at now? I believe it would be right at the water line. It should be boundary between your shore and your coast. Yeah, it should be right at the water line. Okay, so your terminology that you should be aware of. This is probably more than you need to know for the exam, but essentially the main ones that I'd want you to know about is where your coastline or your shoreline would be, where your coast would be at, where your shore will be at. So you have your back shore and your foreshore. So your foreshore will be within the water primarily, and then your back shore will generally be on the beach itself. You can have berms, sometimes you can have sea cliffs, sometimes you'll have a storm scarp that's basically a berm where which is created from storms. You'll have a beach face. Sometimes you'll have a terrace within the ocean. You can have a longshore trough and a longshore bar, and a storm bar. So storm bar will be when the storm pushes sand out into the ocean, and that's where it will temporarily sit until the storm is over and the waves can push it back onto shore. So let's see. So yeah, that's pretty much the main ones that I want you guys to know about. Beach composition. The beaches, so the sand from the beach is primarily comprised of material from the local area. So here in Hawaii, where do you think our sand comes from? It's a nice light tan, whitish, I guess you could say, in color. And so our sand comes from corals primarily. So whenever the coral breaks down, or we have biology that breaks it down for us, like the parrotfish, they will break down the coral and produce sand for us. So that's where primarily all of our sand comes from. But if you see, if you've ever been to a black sand beach here in Hawaii, that black sand is created from lava rock that has been broken down into smaller pieces. All right, so typically you'll see that in areas where you have volcanic activity. So here in Hawaii, that's on the Big Island, but I know you can still find some black sand, I think in Maui, even though there is no volcanic activity over there. They still do have remnant lava flows over there. And then here in Oahu, we have, I know in Kaneohe Bay, there's a beach that is more pebbly. And so that's generally created from the rocks in the ko'olaus, so in the mountains. So when you go to the northwestern states like Washington and Oregon, they typically will have pebble beaches, and those pebbles are from the Rocky Mountains primarily, right? So I know here in Hawaii we also have green sand. I don't know if you guys know, but the green sand is, well, actually you guys should know from the marine sediments lecture, right? Well, green sand is comprised of olivine stones. It is a green gemstone that is created when lava is formed. So under the right conditions, it can create this green gemstone called olivine. And here in Hawaii, we do have a couple of green sand beaches, and one you can actually see here in Oahu. If you go to Diamond Head, and if you go to where the lighthouse is at Diamond Head, and you go down to the beach there, you can find some green sand over there. And then we also have some red sand. Red sand we can find here in Hawaii on Maui. And that red sand is primarily made from the red rock material that you can find in the surrounding areas. So let's just say Mililani was near the coastline. If that was the case, it would create a red sand beach because of that material. That soil over there is red in nature. And then around the world, you can also find pink sand beach. In New Zealand, I can think of one, and that beach is primarily made out of seashells. So primarily oyster and scallop seashells. So that's a pretty nice beach to go to. Beaches that have finer textures will typically be in low impact areas, so you can assume that that beach doesn't get a lot of wave activity. So for example, Lanikai Beach in Kailua, that has a much finer grained sand than say Sandy's, and that's because the wave activity over in Lanikai is much it's lesser to an extent than Sandy's. Because when you go to Sandy's, you should expect a larger grain sand type over there. And beaches, materials from the beaches are in transit, or are transported along the shoreline. So when you look at a beach, most people would think that the material on the beach just kind of stays put, right? Well, it doesn't do that. It actually moves along the shoreline. So whichever way the current is going in the water, it will transport sand along the shoreline. So let's just say you have point A and point B, and the current is traveling from point A to point B. The sand will travel from point A to point B because of the current, and I will show you that in a couple of slides. So there's a couple different types of movement along the beach. So you'll have your forward and backward movement, which is basically the water coming onto shore, which is swashing the beach. So that swash is the water that comes onto the beach and soaks into the sand. And then any water that goes back out into the ocean, that would be known as backwash. So that's the water that after it soaks into the sand, it doesn't stay in the sand. It comes back out and drains back into the ocean. So during the summertime, this swash and backwash cycle is very minimal, and a lot of that sand stays on the beach. So that's typically when you'll see a lot of light wave activity during the summertime, and you tend to have more swashing and less backwash. So the sand on the beach stays on the beach. That's why during the summertime you have really nice beaches, whereas during the wintertime you tend to have more wave activity. So your backwash is greater than your swash, and that tends to transport more sand into the ocean. Now, that sand that's at the sandbar in that profile, or in that image on the right hand side there, that doesn't stay there. That's only temporary. Once it goes back to the summer profile, it goes back, it sends the sand back onto the beach. So it's a cycle of the sand going out and the sand coming in. All right. So this image right here is how the sand is transported along the beach. So you have your wave coming in at an angle here. So your wave approach is in blue, so it's coming at an angle, and then as the wave retreats, which is a green arrow, it takes sand with it into the water. And then when another wave comes by, it pushes that sand back onto the beach, and then as the wave retreats, it takes more sand, and so forth until all of that sand has moved one space down. So I hope you guys understand that. But essentially, that the resultant force in this case is your longshore current. So that longshore current then moves sand from point A to point B. So it does this kind of zigzag effect where sand or water comes onto shore, sand goes out. Water goes onto shore, deposits some sand from the previous point, and then the water goes out and it takes some sand from that point, and so forth and so forth. Okay, so there are two main types of shorelines that you can have along a coastline, and depending on the amount of wave energy found along that shoreline will determine whether you have erosional shores or depositional shores. And so erosional shores will typically have well-defined cliffs and will typically be within high tectonic activity areas, but essentially erosional shores are where you see a lot of wave activity. Your depositional shores are quite the opposite. They are not found in high tectonic activity or high wave activity areas, and so they tend to have more sand deposits, and they typically will have barrier islands along the coastline. So this image right here is that of an erosional shoreline You can see that the cliffs that this particular coastal line has, they have some beaches, but these beaches will tend to be more rocky and larger grain sand. Some of the features you'll see are headlands, you have embayments, you have tombolos, sea caves, wave cut notches, gravel beaches, pillars, let's see, sea stacks, and sea arches. So as you see in the bottom image right there, that notch, wave cut notch, is created when you have your waves coming in and it's hitting the cliffside and it's slowly wearing away at the cliffside. So eventually, when it erodes away enough material, that the top part of that cliffside is just going to collapse into the ocean. But it could, if it's coming in from the side, and let's just say it's cutting into that headland part, that sea arch there is created from a wave cut notch. So that whatever the case may be, that headland, that area where the sea arch is weaker, and so the waves were able to erode it much more quickly than that future sea stack. But if the waves continue to erode that sea arch, and say the top part of the arch erodes away and falls into the ocean, well, that point over there, which is called the future sea stack, then becomes a sea stack, right? So essentially, and then that tombolo is just an eroded part of that headland that basically fell into the ocean and became material. So in that case there, you have a lot of wave activity moving material around. Well, in the previous slides, I forgot to go over the different features within a depositional shoreline. But in that depositional shoreline, you can see there are features like barrier islands, beaches, sand spits, bays, lagoons, a lot of different stuff. You also see tombolos in depositional shores too. But yeah, so go back and take a look at that. Sorry, I forgot to mention that. But the three main, what your textbook likes to call compartments, but essentially the steps for which material gets from land to the deep ocean, there are 3 steps to that. So I highly recommend you remember what these 3 steps are, as they may appear on the exam. But essentially the 3 steps are rivers, beaches, and submarine canyons. All right, so step 1 starts with rivers, and the rivers supplies the material to the beaches. So the material from the mountains that is eroded gets transported to the beaches by the rivers. So that's your step 1. Step 2 are the beaches itself, because on the beach itself, it transports material via the longshore transport, or the longshore current. So that longshore current will transport material from the beach into the submarine canyon. And then step 3 is your submarine canyon, and that's what moves material from the beach into the deep ocean. Okay, so that is your cycle of material going from land into the deep ocean. All right, so there's also a thing called beach starvation, and this is essentially when you're starving the beach of material from the mountain. So you're cutting off step 1, and when you cut off step 1, you then reduce the amount of material that's going to the beach, and you basically eliminate step 2, which then does not allow any material to go to step 3 into the deep ocean. So some ways that humans, and this is all because of humans, you don't find this in nature. Humans have done this a number of different ways. They have done it through dam construction, concrete lining of rivers, longshore transport. Well, longshore transport is a natural thing, but essentially what humans have done is cut off the longshore transport. You have shoreline hardening, and you have jetties and rock walls. So let's look at each one. Oh, wait, sorry. We'll go back to those types of shore beach starvation types. But first, let's talk about your shoreline types. So this is different from the other one where you have depositional and erosional shores. You can have emerging and submerging shorelines. And so your emerging shoreline is a shore that rises above the sea level. So right now, here in Hawaii, Waikiki is currently above sea level. So that's not to say it's an emerging shoreline, but if Waikiki were to continue to rise above sea level, then that would be considered an emerging shoreline. So if it continued to rise, right, that typically those types of shorelines have characteristic marine terraces and stranded beach deposits, because essentially the coastline is rising. So as the coastline rises, that beach continues, the original beach continues to get further and further away from the coastline. So then it no longer becomes a beach. It just becomes part of land. Versus you have a submerging shoreline, and that's where the shore is sinking below sea level. So in majority of the coastlines cases here in Hawaii and around the world right now, because of climate change and we're heating up the global temperature, that's causing the sea level to rise, which is causing a submerging shoreline case in almost all areas. So Waikiki Beach is an example of a submerging shoreline, because if the sea level rises, as it's anticipated to do, it will cause drowned beaches, submerged dune topography, and drowned river valleys. So because Waikiki Beach is a swamp area, it will get flooded, and the beaches that are along the shoreline right there will be considered drowned beaches because it's underwater. It's no longer a beach anymore. All right, so changes in sea level can occur naturally, as well as not because of humans. But naturally, you'll have these three types. You'll have tectonic movement, isostatic adjustment, and eustatic adjustment. And changes in sea level that happen naturally tend to be caused by the movement of Earth's crust. So that's the reason why those three right there are the reasons why. And movement of the crust in relation to the shoreline changes the sea level. So over time, there have been a number of different changes to sea level, to the coastline. And sometimes the coastline or the sea level is higher. So the coastline, because the sea level is higher, it takes up more of the land space. So the coastline is further inshore, versus if the sea level was lower, it would expose more land, right? Because the continental margin is just part of the continent that is submerged. And so more of that continental margin will be exposed and more land will be exposed. So the shoreline will be further out. All right, let's talk about these three main types. So your tectonic movement, basically you'll have crust movement due to tectonic activity. So you have your passive and active margins. Passive margins tend to have submerging shores because sediment accumulation occurs along the shoreline, and that puts more weight on top of the land, which then submerges it. versus active margins tend to have emerging shores because you have an upheaval of the crust due to volcanoes and volcanism. So that's where you tend to see more uplifting of the material. But then you can have isostatic adjustment, and that's where the crust will sink under large heavy loads of ice or sediment. And once that sediment or ice is removed, then you have what's known as a rebound, and that crust will then rise back to its original height before the heavy load was put on top of it. And so that's typically what you'll see happening when glaciers melt. And so there's a very good example, I believe it's in Scandinavia, where you have an emerging shoreline. It's coming back up, and so you have more land on the coastline emerging every year because that glacier, which was from back in the last ice age, melted some number of years ago, and so that land now is slowly starting to rebound and come back up. And then you have eustatic adjustment. This is when you have changes in ocean volume. So essentially what we're doing right now with climate change. And if you melt a lot of the glaciers and a lot of the sea ice, and you put that water back into the ocean, you are changing the sea level. And you can do this either by glacier melt, the speed of mid-ocean ridges. So if that mid-ocean ridge speeds up, then that means it's spewing more material into the ocean, which then is causing that mid-ocean ridge to rise higher, which then is displacing more water. Or you can get the creation or destruction of lakes. So if all of that water that's found in lakes goes into the ocean, then you are rising the sea level. So take a look at that comic there, because that's a pretty funny one. But yeah, the image on the bottom there is just a depiction of what's happening to a glacier. So back in 2008, it was melting, but it was melting at a slower rate. But by the time 2014 came along, so that's what, so 6 years later, just in that time span, it's decreased by more than half its size. So that's a pretty significant amount of ice to melt away. And all of that water is going into the ocean. Okay, so shoreline stabilization. So because of all these changes in the coastal region, and especially here in Hawaii, tourists come here because of our magical white beaches, and they want to be able to bask in the sun any time of the year. We tend to have to do specific things in order to keep our beaches nice and pristine. And so what the state has done is erected some what they would consider protection for the shoreline to prevent erosion and the movement of sand. And so while you're going through this lecture here, I want you guys to keep in mind that shoreline stabilization is a nice idea, but when you mess with that longshore transport, it messes everything up. So the main things that we have done to try to prevent sand from moving and from erosion occurring on the shoreline is erecting growings, jetties, breakwalls, and seawalls. So a growing is a wall perpendicular to the shoreline that traps sand. And I have images on the next slide for you to see. A jetty is a wall perpendicular to the shoreline that protects a harbor entrance. So typically you'll see two jetties. So whereas a growing is just one wall that extends out into the ocean, a jetty has two walls that extend out into the ocean. You have your breakwater, which are parallel to the shoreline and protect the harbor entrance from incoming waves. And then you can have seawalls, which armor the shoreline using a wall, right? So you basically are taking away the beach completely in that case. So on this next slide here, you can see the differences between each type. And the top left-hand image there is that of a that's a breakwater. And as you can see in that case, all of the wave energy is hitting that seawall on the outside. So once you get into the harbor, you don't have any wave energy whatsoever. The water is calm inside of the harbor. So that's the primary purpose of a breakwall. The bottom left-hand image there is that of a seawall. So right there you can it's basically just a wall on the beach that protects the land from erosion from the water and the waves. So in this case right here, you are cutting off that beach from getting material from the mountains. So eventually that beach will completely erode away and no longer be there anymore. In the top left-hand image with the break wall and the harbor, I forgot to mention that all of the sedimentation that occurs within the harbor is because that wave activity that normally comes in and takes that sediment away is no longer there. So that harbor will eventually need to be dredged out from all of that excess sedimentation that's occurring, because that material is coming in from the mountains, but it no longer has its ability to go out into the deep ocean anymore. So it just stays in that harbor. The image on the top right-hand corner there is that of a growing. So that's just a single wall that extends out into the ocean. And as you can tell, the sediment on the left or the right-hand side of that wall is accumulating, and the sediment on the left-hand side of that wall is eroding. And what I want you to keep in mind in this instance is the longshore transport in this case is going from the right-hand side to the left-hand side. So that wall is cutting off that transport. So that wall no longer allows that sediment to move along the coastline. So it gets stopped at the wall, but that longshore transport doesn't just stop because the wall's there. It still picks up the sediment that's to the left of that wall and moves it along the beach. So you have more erosion occurring on the left-hand side and more deposition occurring on the right-hand side. And the reason why they're doing this is because they don't want the sand to move. But really, they're causing a huge problem, because if they just remove the wall and let the beach do its own thing, it would even out. But now you have more sand on one side and less sand on the other. Okay. Now the image on the bottom right hand side is that of a jetty, and you can see the two walls that extend out, and this is meant to protect the harbor entrance right here. And what I want you to see is that the longshore transport in this case also goes from right to left, because you can see the right hand side there has more sediment than the left hand side. What you can see here is that the jetty actually broke on the left hand side, so now it's letting sediment into the harbor entrance, which is what they wanted to prevent first off. So they would have to go over there, dredge that area, put it back onto land if they really wanted to, but that would be a lot of money to do that. But essentially you can see if they didn't have the jetties in this part right here, that sediment would close off this gap and it would no longer be a harbor entrance. So by putting the walls up, they're preventing that sedimentation from closing up this gap. Okay, so now there are some alternative methods to shoreline hardening. Um, Keep in mind, most likely these solutions would not be implemented because they would not align with social aspects. But essentially, the three main ones would be restrictions on construction near coastal region. So if you didn't allow building permits to build near the coastal area, you wouldn't need to harden the shoreline. Beach replenishment, essentially bring sand from another area and deposits it onto the beach where you want to keep it a beach. And this one I have an issue with because if you just let the beach go and do its thing, it will be a beach at some point during the summertime. But again, here in Hawaii, especially on Waikiki, every springtime they do a beach replenishment of Waikiki Beach because during the wintertime a lot of that sand goes out, and for the tourists they need to have the beach right then and there. And then thirdly, you have relocation, and that's essentially moving structures away from the coastal region. And while this is not often done, it is done in certain cases. But majority of the time, most people would not want to do this. Some characteristics of coastal regions are there is a defined halocline near the shore. And a halocline, remember, is a rapid change in salinity from the surface to the deep ocean. And so this halocline is there because of a lot of freshwater runoff that occurs in the coastal regions. And this brings lower salinity waters at the surface. You tend to have higher rates of evaporation near coastal regions because the water is shallower. And so during the daytime, especially like say here in Hawaii, our coastal regions experience high rates of evaporation because the water is shallower, and we have very little cloud cover to protect the ocean. So a lot of water from the ocean evaporates. And then you tend to have a lot of mixing. So you tend to have very similar conditions throughout the water column. This is typically found in the winter times, especially here in Hawaii, where you have high winds that are mixing the water column. So you have oxygen levels that are the same throughout the water column, or you have salinities that are the same throughout the water column. Whereas during the summertime, you tend to have haloclines and thermoclines forming because you don't have that wind mixing. So you have warmer temperatures at the surface and cooler temperatures at depth, and so forth. And temperatures will vary depending on where you are on Earth, and where the coastline is. So, for example, here in Hawaii, our coastlines tend to be much warmer. So that's the reason why people like to come to Hawaii, because at any time of the year, you can go down to the beach, enjoy some sun, go for a swim. Whereas if you were to go to a beach in California or even Alaska, that would get kind of cold, normally speaking. All right, so some other features that you can find along the coastal ocean are estuaries. Estuaries are partially enclosed bodies of water where fresh water dilutes the salt water within this body of water. So typically river mouths, bays, inlets, gulfs, and sounds are all examples of estuary. Here in Hawaii, Kaneohe Bay would be known as an estuary because it is a bay and it is getting fresh water from the rivers and salt water from the ocean. All right, so there are 4 main types of estuaries that you can find around the world. The 4 main types are coastal plain estuaries, fjord, bar-built estuaries, and tectonic estuaries. So we will go, I have a photo of each of these on the next slide. Yes, Road. And Rowan is trying to touch my computer right now, so I apologize for any noises he makes right now. But a coastal plain estuary is a flooded river valley, and so that river valley will flood up with fresh water, but then it will have salt water coming in, so part of it will be brackish in nature. So the salinity of estuaries are brackish water, typically speaking. All right, so they'll be anywhere from 5 to 10 parts per thousand in salinity, all the way up to like 20, 25 parts per thousand salinity. When you have ocean water, the average salinity of ocean water is about 35 parts per thousand, and the salinity of fresh water can range anywhere from 0 all the way up to 5. And then you have a fjord. A fjord is a flooded glacier valley, so typically these tend to occur in colder climates where you have glaciers. You have a bar-built estuary. Oh, kablooey. Wow, that was pretty messy. He just got snot all over the place. Okay, and then bar-built estuaries are barrier islands that separate the lagoon from the ocean. So keep in mind you still have the connection to the ocean, because you still need that salt water coming in, but you do have fresh water coming down from a river. And then lastly, you have tectonic estuary. This is when a body of water is semi-enclosed away from the ocean, and that's because of the uplifting of the crust from tectonic activity. All right, so let's look at this. So on this slide here, you've got 4 different images. The slide on the top left-hand corner there is an example of a coastal plain estuary. So you can see on the left-hand side of that image is where the fresh water is coming in from that stream. And then you have the ocean, an inlet to the ocean, and that ocean water is coming in, and the estuary is basically that pond right behind the beach there, where the salt water and the fresh water are mixing. And then on the bottom left-hand corner is an image of a fjord. This is where the glacier would have been when it was fully developed, but when the glacier retracted, it let ocean water in, and so the fjord, the fresh water from the glacier is coming down the valley, and then the ocean water is coming in and mixing. So you have a diluted saltwater mix within this valley here. Then the bottom right-hand image is an example of a bar-built estuary. You can see the sandbar that is built up in the first image, and you can see there's still an outlet to the ocean. So the water at point A is fresh, and the water at point B is salty, and the water in that lagoon area in between A and B is the estuary itself, because it will be a diluted seawater mixture. So you can just see a top view and a profile view of what it would look like. And then the top right-hand image there is that of San Francisco Bay. That is a prime example of a tectonic estuary. So the bay itself was created due to tectonic activity. The land near the ocean uplifted, enclosed that bay part itself, and so with all of the fresh water that it gets from the surrounding mountains and the ocean water from that thin inlet right there, that's what creates a tectonic estuary. So there's different types of mixing that occurs in an estuary, and depending on the depth and the formation of the estuary will determine whether you have vertically mixed estuary, whether you have slightly stratified, highly stratified, or if you have a salt wedge. And I have images on the next slide again. But a vertically mixed estuary is typically shallow. The flows proceeds from the head of the mouth, so near the river, and will uniformly vertically extend towards the ocean. So each vertical profile that you go away from the river mouth will get saltier and saltier, right? Trust me, it'll make sense on the next slide. And then next you have slightly stratified, which is somewhat deeper than a vertically mixed estuary. The flows created are in a circulation pattern, so you'll see a little bit more vertical, how do you say, salinity profile. So it won't all be the same salinity as you go down. It may vary a little bit. And then you have highly stratified estuaries, which are deep lagoons. And these ones have a similar salinity at the surface, but a different salinity at the bottom. And then you have, well, I shouldn't say highly stratified. It'll be similar salinity to the ocean, but you'll see in a sec. And then salt wedge has high river volumes, so there's no vertical mixing whatsoever. So you'll have a different salinity at the surface and a different salinity at the bottom. Okay, so in this example right here, this image is straight from your textbook. Image A, which is the top left-hand corner, is that of a vertically mixed estuary. So you can see the head, which is the mouth of the river, and the mouth, which is the ocean side. And you can see as you go away from the river, the salinity increases, and it's the same throughout the entire water column. So in this case, the flows from the river and the flows from the ocean equal each other, okay, and are well mixed. In B, which is the top right-hand image there, that's of a slightly stratified estuary, and so you have basically a vertically mixed estuary, but the river flows are a little bit stronger, and so you tend to see like an angle to the salinity measurement as you go down in depth. And then in C, you have highly stratified. So this basically means your ocean water is coming in faster than your river water. And so the ocean water stays at the bottom of the estuary, and your fresh water floats on top, and it quickly, because it's not flowing as fast as the ocean water, it stays on top, doesn't extend down to depth, and by the time you get near the mouth of the river, the ocean, once you get near the mouth of the ocean, it's primarily all ocean water. And then D is your salt wedge. So your salt wedge, your river, the head is flowing much faster than the ocean. So you will have more fresh water in the estuary than in the ocean water. Lagoons. This is essentially where the estuary is at. Typically, bar-built estuaries will create lagoons. They are shallow bodies of water, and they will have 3 different zones within the estuary. They will have a freshwater zone, which is closer to the river. You'll have a transitional zone that will be where your ocean water and your freshwater meet, and then you'll have an area where there's primarily only salt water. And then you can also have marginal seas, and these are large, semi-isolated bodies of water. They still need to have a connection to the ocean because they can be estuaries or they can be totally saltwater. But these are typically created by tectonic activities. So your Mediterranean Sea is a good example of a marginal sea. And you can see it has different basins, and depending on how close it is to the inlet by the ocean, which is the Gibraltar Strait, that that area over there will be, well, will be saltier. But in this case, the basin that's furthest away from the ocean water is saltier because it experiences higher rates of evaporation. So it really just depends on the climatic change, climatic conditions of the area. All right, so this was chapter 10. Stay tuned for, I think it's chapter 15, 14 or 15, I forget. But that's when we talk about marine pollution. All right.